Okay, so in this particular video, I'm going to show you how to use different strategies to solve for all these different parts. So if you want, pause the video, read it, get a scenario in your head. Okay, all right, so here we go. So here we have a scenario where you have an object moving to the right with a velocity of positive 28, and then it's going to slow down and come to a complete stop, and the distance given here that's required to do so is 70 meters in the diagram. Okay, so initial velocity is positive 28 as indicated by the vector arrow there. Your final velocity, aka v of t, is 0, and the distance is 70. So let's knock out part A and B. All right, and I do want to make a point. It's important that you listen to the different strategies and then apply one that makes the most sense to you. And hopefully as you practice, things get better and quicker and more accurate. All right. So listen well. Let's do part A. The question asks you to find the acceleration of the car, or aka in this case is going to decelerate. All right. So the first strategy that I think is quickest is this particular function in kinematics: vf squared minus vi squared equals 2a delta x. Why? It's because you have a bunch of information already. So as you learn to read schematics, identify what's given and what's not given. Here, it asks for A. I know VF is 0, VI is given. My delta X is given as 70, or if you want, positive 70 because it's moving to the right. So really, at the end of the day, I want to cross out VF squared because it's 0. I want to reduce that function. I want to carry the negative sign down. So it'll be negative VI squared equals 2A delta X. And then to solve for A, I would need to divide both sides by 2 and delta X. And by doing so, the 2 and the delta X on the right side cancels out. And then that's going to move to the left side, and that's going to go in the denominator. Therefore, I have a simplified version of A. Again, learn to isolate for the variable that's being asked. In this case is A, so I will isolate it, aka get it by itself. So A is going to equal to negative VI squared divided by 2 delta X. Here I have VI is 28. Don't forget to carry down the square. 2 is part of the function, and then delta X in this case is a positive 70, but I'm just going to use 70 just because we are 70 and positive 70 is the same in terms of calculation. All right. So if you simplify that in your calculator, you should get a value of negative 5.6 meters per second squared. So that is your acceleration. I do want to remind you that acceleration is a vector, so it's appropriate to include the direction. In this case, the negative sign implies that the acceleration vector is going to be pointing left, which makes sense because if you look at the diagram, if the car is moving to the right and for it to slow down, you need some sort of opposing force, aka opposing, in this case, would imply moving leftward. So your acceleration vector needs to be negative in this particular problem. All right. Now, therefore, what if? Okay, what if you don't have this first strategy function in your head? What if you went straight to this function here, which is average acceleration is equal to change in velocity, or Vf minus Vi over change in time? And that's okay. To find A, you need a bunch of variable here, Vf, Vi, and delta t. Well, we know Vf from the schematic and from the statement is 0, so we can cross that out. So I'm just going to carry the negative Vi squared, the negative Vi down to the next step here, and delta t. Here, I noticed that I have Vi already because the problem said so is 28, but delta t, I don't know what delta t is. I don't know how much time it took for the car to come to a complete stop because they never gave it to me directly, but that's okay. So you notice here what's holding you back if you had applied this strategy is your change in time. How much time did it take for the car, to come to a stop or travel 70 meters in this case? But that's okay. It's okay if you're stuck. Just go find it using a different kinematics equation. Here, I decided to use the average velocity function. Now there's a reason. Well, one, it has t in it because I need to find t, and I know my delta x, I know my vi, and I know my vf. So this particular function is super useful in terms of trying to find t if enough information is given. All right, but to find t, I know it's here. T in this average velocity function is in the denominator. I need to flip it so that it's in the numerator. But if you flip the left side, you got to flip the right side as well. But here we go. Vf is equal to 0, so I'm just going to cancel that out. Okay, so I'm going to flip the whole function upside down. So therefore, t is now in the numerator, delta x is going to be in the denominator, and then 2 is now on top, and vi is on the bottom. But to get delta t by itself, I need to multiply both sides by delta x to get rid of it. So therefore, t is going to equal to 2 divided by vi times delta x. I know my vi, I know my delta x. Vi is 28, delta x is 70. So if you punch all this in your calculator, you should get a time of 5 seconds. Well, you just found time, so just substitute it in for what you were missing if you had used the average acceleration equation. Okay, so A would now equal to negative 28 meters per second divided by 5 seconds, and then 25 divided by 5 will give you a value of 5.6, and don't forget the negative sign, so therefore the answer is the same, negative 5.6 meters per second squared. Okay, so that's that. So to show you that there's different strategies, which one you take, it all depends on your brain sees these types of problems, and then kind of move on with the quickest strategy. Now, hypothetically speaking, okay, what if you didn't do part A based on my middle strategy there? You know, what if you did part A using this particular strategy here, okay, on the left side? Well, to do part B asks how long does it take for the car to come to a stop? Well, in this particular case, well, to find delta t, I notice again delta t here is in the denominator on the right side. I have an A on the left side. To find delta t, I need to cross multiply both sides by delta t and then divide both sides by a. So that's going to leave me with this function. I went ahead and cross out vf again because it's 0. I carry down the negative sign. So here we have delta t is equal to negative vi over a. And we know that vi is 28. We know acceleration from part A, which is negative 5.6. And then once we just plug this in, we can simplify it. The negative signs will cancel out. And there it is. The answer is 5 seconds. However, had you used a strategy for this particular part A, with A is equal to VF minus VI and T, in which you didn't know T, you actually accidentally found the answer to part B by doing the strategy. So if you notice here, if you had gone this route for part A, you would need to find time, but finding time, which is 5 seconds, actually is the answer to part B. Okay, so sometimes coincidence happen based on how you view things. You can actually find multiple answers based on the work that you do. So if you did this part, you actually found the answer to A, and you also found the answer to B. Okay, so that's just proof to you based on what it is that you're doing. You can find answers, variety of methods. All right. Now, the other way to do it is flip the image. I know the problem sets that there's a car moving from left to right. Its initial velocity is positive 28 meters per second, and it comes to a stop. However, what I can do though is I can actually reverse the situation where I can have the car starts from rest and it's going to accelerate leftward to a speed of 28, or in this case, a velocity of negative 28, because velocity in this case is moving leftward. Now, why would I want to do that? I can do that to find time because, well, I can apply my displacement function. So this is just a little trick. If you like it, use it. If you don't, discard it, okay? I want to let the car start from rest, and then I'm actually going to have it speed up to a velocity of negative 28 meters per second. By doing that, in your displacement function, the VIT term disappeared because now I'm treating VI as 0. So you know a bunch of information already. Well, the car is now going to accelerate leftward for a distance of 70, but delta x is your displacement. So in this case, the car is moving left, so I would just add a negative sign, negative 70. The acceleration you already found in part A, which is negative 5.6. So you notice here in the statement, the only thing we don't know is our t squared. So if you simplify this stuff, okay, 1/2 times negative 5.6 reduces down to negative 2.8. And then to get t squared by itself, we divide both sides by negative 2.8. By doing so, you're going to get t squared is equal to 25. Well, this is t squared. So to get just t, we need to radical both sides. Radical both sides would leave you with just t on the side because the radical symbol and the square is going to cancel out. And then square root of 25 is simply 5. Okay. So as you can see, by doing this little trick, I can also find the time that it takes for this physical phenomenon to occur, and it's very consistent. It also takes 5 seconds. So it doesn't really matter how you see these problems. The answer is going to be the same if you do the physics properly. Okay. All right, let's move on to part C. Part C asks us how long does it take for the car to cover the first 35 meters? Okay. Now, well, I'm just going to start with the average acceleration function here. Why? Because it has a t in it. To get t by itself, again, I'm going to multiply both sides by t, divide both sides by a in the same step. So the function that I start with is going to look like this. Here, I want to point out though, it asks us to find how long does it take for the car to cover the first 35 meters. Well, you need to recognize that at 35 meters, the car is actually moving, okay? It only came to a complete stop after 70 meters, but this question is not at 70 meters, it's at 35, which is the midpoint, which suggests that the car is indeed moving. So VF here is not 0, so that's vital. So do not plug in VF as 0 just because the diagram said VF is 0. You have to recognize where the problem starts and stops. In this case, it starts at 0 and it ends at 35 meters. So at 35 meters, it's still moving. So I can just plug in stuff that I know. VI is 28. Again, acceleration is given in part A is negative 5.6. Here, I don't know what VF is. I don't know how fast it's moving by the time it has traveled half the distance. But that's okay. You can find this pretty quick, okay? Again, recognize what you need to do based on the information presented to you in the diagram. Here, why would I bust this out? Well, I'm looking for VF. I know what VI is. I know what A is because A is found in part A. And I know my delta X. And what's my delta X? My delta X is going to be here 35 or positive 35. So at the end of the day, you have a bunch of variables already. So to get VF squared by itself, I'm going to move this negative VI squared to the right side. So it'll be 2A delta X plus VI squared. So here I'm just going to plug in values. A is negative 5.6. Delta X is 35 because it's moving to the right. VI is 28 because it's given. I carry all my squares down. And then to get VF by itself, you need to radical both sides. So if you simplify stuff, it'll look like this. And then negative 392 plus 784, okay, it's going to give you a positive 392. And then to get VF by itself, radical both sides. So the square root of 392 is going to give you a velocity of 19.8 meters per second going to the right. Now that we found the velocity, we can just plug it back in for the velocity that was missing. So the car is moving at a rate of 19.8 meters per second by the time it gets to the 35 meter mark. Well, you just found VF, substitute in. So VF is simply replaced with 19.8. And then from there, we just simplify our calculator work. And then you'll get a time of about 1.46 seconds, okay? So that's how to do this one. Again, you notice here it's 2 steps, which is okay. You don't get intimidated if you run into unknowns. Think about how to unlock these types of problems, right? So I do want to point out, so this is crucial, mistake that kids often make or folks new to physics often make is that they make false assumption. We know from the other part that it takes a total of 5 seconds to cover this 70 meters. Kids will often say, well, to go halfway, it'll take half the time. And that's a big misconception. It does not take half the time. Okay, so the answer here is not 5 divided by 2. Why? Because the car is moving at a fast rate when it first starts. So therefore, because it's moving fast, to cover the first half of the distance would take less than half the time. Okay, if you're moving fast, to cover distance require less time, and then by the time it slows down to the midpoint where it stops, the speed is slower. So if you're traveling slower, it will take you more time to travel the same distance. So my point is that do not simply take the total time and chop it in half just because it asks for half point, and that's a big no-no. So think about what I just said. Hopefully it makes sense. Okay, I'm expecting an answer in this scenario less than 2.5 because I'm moving fast. To cover the first 35 requires less time because I'm moving faster. All right, listen again if you need to. Let's go part C again. All right, so again, this particular part asks you how long does it take. So I can flip my image. I can flip my image again. I'll start with the car at rest and I'll get it to go 70 meters to the left, and then it'll reach the same speed. So my final velocity is what's the initial in the initial problem. All right, keep up with this strategy. If you like it, use it again. If not, discard it, okay? I can use my displacement function. The reason I can use my displacement function to find time is because I just made my VI 0. If I made my VI 0, this VIT term is going to disappear from the function, which simply reduces down to delta x equals 1/2 AT squared. Well, I know my delta x, okay? My delta x is negative 70 for the whole entire thing. My acceleration I already found in part A, which is negative 5.6. Okay. Now if you simplify this, 1/2 times negative 5.6, you get negative 2.8. And then to get t squared by itself, divide both sides by negative 2.8. You'll get t squared is equal to 25. And then to get t by itself, square root of both sides, and then the square root of 25 is going to give you 5 seconds. But it's important that you learn to interpret the information that you find. Otherwise, it'll be no good to you. So this t that's equal to 5 seconds tells me, well, it's going to take the car a total of 5 seconds to cover the first 70 meters. Okay, so there's my 5 seconds. But the question didn't ask for that, right? It asked for how much time is covered from 0 to 35. So therefore, what I can do now in this diagram that I flip, I can actually find how much time it takes to go from 0 to 35 leftward. So therefore, if I do that, my VI once again is 0, but this time my delta x is going to be negative 35. A is still the same, negative 5.6. Simplify this stuff will give me negative 35 is equal to negative 2.8 equals to t squared. Dividing both sides by negative 2.8, it's going to give me t squared by itself. So negative 35 divided by negative 2.8 is going to leave me with 12.5 seconds squared. To get t by itself, radical both sides, and then the square root of 12.5 is going to be 3.54 seconds. But this is not your answer, because I flipped the image. The time that it took to go from 0 to the first 35 meters going backward is 3.56. So therefore, to find this time, I would just take the difference. Okay. Why would I need this time? Because in this diagram, it's from left to right. So I need to find this segment. So therefore, to find the time, I simply would just take 5 minus 3.54, and that would give me what the time of 1.46, which is the same answer as the previous strategy. I like doing this because it allows me to cancel my VIT and my displacement function. But if you don't understand what I just did, again, stick with the strategy that you're comfortable with, that you're confident with. Okay. All right. So let's do part D. Part D asks us to find the ratio of distance between 0 to 1, and then question mark the distance between 1 to 2 seconds. So to do this, we need to find our displacement function. Okay. But well, to find distance is pretty straightforward. You need to use your displacement function because the car is just moving to the right. It's moving one way, okay, at least for this diagram. And then you need to be able to figure out what VI is, okay? For this one, the statement on the left starts at 0 second and goes to 1 second. So my VI is going to be 28 because the car is already moving at a time equal to 0. It didn't start at rest. Actually, for this one, it starts moving already. My time interval is 1 second because from 0 to 1 second is 1 second. My acceleration, I just carry from the previous parts. And then my time interval here is 1 second. By doing so, I can find the distance covered during the first second. Pretty straightforward, okay? So if you simplify your calculator work and then to sum up stuff, it should give you 25.2 meters. And then we can use the same strategy. Again, apply the same function, but just make sure you pay attention to the different initial and final points. Here on the right side, the problem starts at 1 second and it ends at 2 seconds. So it's important that even though you have your displacement function correctly, it's essential that you look at the statement and use the proper VI. Here, your VI starts at 1 second. So therefore, if you look on top of my screen, I have all these values written out, which is pretty easy to do. Acceleration is negative 5.6. What that tells me is that the velocity changes. In this case, it gets smaller by 5.6. So 28 minus 5.6 is 22.4. Okay. Therefore, at 1 second, the car has slowed down from 28 meters per second to a velocity of 22.4. This is now my initial velocity in this strategy. So therefore, my VI, I'm going to use 22.4. The time interval is 1 second because from 1 to 2 is 1 second. This is just now plug and chug. So if you simplify it, you'll get 22.4 plus negative 2.8. And if you simplify that further, you'll get 19.6. Okay. Now, all you have to do is just set these two statements equal to each other with the a little heart. So here I have 25.2 on the left side equal blank. The blank takes the place of the question mark, and you can keep the question mark as a variable. In this case, I like to use the symbol heart equals to 19.6, which is what we just calculated. Now, to get heart by itself, you simply divide both sides by 19.6. Therefore, heart's going to come out to be 1.29. So the question mark is 1.29. Okay, so that's the ratio between the distance for the first second and the distance of the second. All right, so that's that. Now, if you like, you can do this for part E. Okay, so part E asks us to find the average speed from 0 to 2, and it also asks us to compare the ratio from 2 to 4 seconds. Well, average speed is super easy to do. Average speed is simply distance divided by time. Okay, here to find distance, I want to use my displacement function. If it starts at 0 second and ends at 2, my initial point is at 0. If that's the case, my initial velocity is going to be 28. Therefore, on the top of the screen here, on the right in the green, you notice here I put v of t at 0, which is your initial velocity, is 28. So it's important to keep track of your VI. My VI is 28. My change in time is 2 because the interval from 0 to 2 is 2 seconds. And then the rest of the work is just, again, substitution. So simplify this, you get 56 plus negative 11.2. And you simplify that further, you get 44.8. Okay. Now, well, to find average speed, we need distance divided by time. We just found our delta x, and our delta x in this case is also our distance because without the direction, your displacement is simply the distance traveled in this case. So 44.8 is the distance. The change in time is 2 seconds. Again, from 0 to 2 is 2 seconds, and that simplifies down to 22.4. But you're not done yet. You just found what the left side of the equal sign is. Now it's time to go find the right side of the equal sign. The right side of the equal sign starts at 2, ends at 4 seconds. Okay. So we can use the same function, again, average speed is distance over time, except now we have to find out how far the car traveled between 2 seconds to 4 seconds. Because it starts at 2 seconds, I need to use the correct and appropriate initial velocity. So on the top of the screen here, again, in this case, it's slowing down by 5.6 every second. So it's going to move at a rate of 20 meters per second. It's going to decrease by 5.6 in the next second, which gives me 22.4 meters per second. And it's going to decrease by another 5.6 meters per second. That's going to give me 16.8 meters per second. Okay, so here I have my initial velocity at 2 seconds. My initial velocity at 2 seconds is 16.8. I'll plug that in for VI. My change in time in this case just happens to also be 2 on the right side because from 2 to 4 is 2. So just kind of go with the flow. Make sure you pay attention to the time difference, okay? Things don't always have to be 2 and 2. It just happens for this one that it's from 0 to 2, which is 2, and then from 2 to 4, which is also 2. But it can be any time interval that you want. All right, and if you simplify that on your calculator work, you should get a value of 22.4. So I just found the left side of the equal sign. I found the right side of the equal sign. So I'm just going to go ahead and solve for average speed here by simply using the distance I found, which is 22.4. I'm going to divide that by the time for this one, which is also 2 seconds. So I'll get 11.2. Okay, so you set 22.4 equal to 11.2. Again, the blank is just a question mark. You can keep it as a question mark. We replace it with whatever symbol makes you happy. I like heart, so to get heart by itself, you need to divide both sides by 11.2. So 22.4 divided by 11.2 is just 2. So the ratio is 1 to 2. In this case, your coefficient for heart is just a 2. All right. So now, part E. You can also do this, okay? And I like this one, but for you to do this one, you have to understand this first statement. The car is going one way, so therefore, average speed and the magnitude of your average velocity must be the same. The only difference is that average velocity has a direction, except it's the same magnitude, so why not? So I can say average speed is the magnitude of my average velocity, which means leave out the direction. But I know that the average velocity function for this one under constant acceleration is VI plus VF divided by 2. Or you can say VF plus VI divided by 2. It's all the same stuff, okay? Well, how do you know what VI is? How do you know what VF is? Easy. Look at the time interval. For the left side of the equal sign, you start at 0 and you end at 2. Well, if you've been paying attention, time's equal to 0, the initial velocity is 28. I need to find the velocity at 2 seconds, so it'll be 28 minus 5.6 to 22.4. 22.4 minus another 5.6 will give me 16.8. So here I have my values, okay? And I want to go all the way to 4 seconds because the right side of the equation is going to go from 2 to 4, which stops there. All right, so here my VI is going to be 28. My VF is going to be 16.8. And I want to add that and then divide it by 2. If you do that correctly, you get 44.8 divided by 2, which gives you 22.4. So the average velocity is 22.4 east or right, except the magnitude is just 22.4. So we can say average speed is the same as the magnitude of the average velocity, which is 22.4. And I can do the same side for the 2 to 4 second interval, okay? Except just make sure you use the right velocity. So this says 2 to 4, so I'm going to focus in on my attention here. It says 2, so I'm going to use 16.8, and then it says 4, so I'm going to use 5.6. So my VI is going to be 16.8 meters per second. My final velocity, which occurs at 4 seconds in this case, is 5.6 meters per second. And then divide that by 2, so I want to sum it up, which gives me 22.4 in the numerator, divided by 2, and that's going to give me 11.2. So I just found the left side, the right side, so set that equal to each other with the little blank that takes in place the question mark here, and the question mark happens to be on the right side of the equal sign, which is blank. Replace it with the heart, define heart, divide both sides by 11.2, and heart comes out to be 2. Multiple strategies in this video. Pick one. Make sure your physics statement is correct and true, and you'll be okay. All right, part F. Part F asks true or false. It says the average speed during each second increases as the car decelerates. Well, that's got to be false. As the car decelerates or slows down, it covers less distance during each 1 second interval. If you're going to cover less distance, well, your average speed is going to be less, not bigger, okay? So I'm going to say it again. As the car decelerates, it slows down. If it slows down, you cover less distance per second. If you cover less distance, then it would suggest that your average speed decreases, not increases. So therefore, this statement is false, okay? All right, let's do part G. Part G, super easy to do, okay? This is just a ratio problem. It's just what if the initial speed was doubled to 56? So instead of 28, what if it doubled to 56? What distance would it take? All right, so we like to go ahead and use this function. Why? Because, again, we have a lot of information already. We don't need to mess with time. VF squared minus VF squared equals 2A delta x. I cross out VF squared because it's the same scenario. It's going to come to a stop. But instead of moving at a rate of 28 meters per second, it's now going to move at a rate of 56 meters per second. Okay, so what I have here is VF. I cancel it out. I carry the function down, and then I isolate for delta x. Now, why would I want to do that? Because the question in this part G asks us to find the distance. And distance is the magnitude of your delta x, because it's moving one way. Here, okay, I have initial velocity, which is now 56. I want to square that. I want to divide it by 2 times negative 5.6 because it sets under the same acceleration. So whatever acceleration I found for this problem, I'm going to keep it throughout. So if you do that and you simplify your answer, it'll come out to be 280. Now, I like to point out that delta x is 280. Well, it's not a coincidence. Well, 70 times 4 is 280. Okay, so it's important that as you play with physics kinematics equation, understand what it depends on, what it does not. So watch what I'm circling. Delta x depends on VI square. The VI term is being square. The 2 and the a on the bottom are just constants. So what's most important in this function is the VI square. Well, if you're going to double the VI, but that VI term is being square, so doubling would imply that the answer comes out to be 4-folds because 2 square is 4. So VI's term is square. It's not a linear function. Okay, sometimes kids have a misconception. If you double the speed, it takes twice the distance. That's a no-no. Doubling the speed does not double the distance. It quadruples it. And why is that? Because VI is being square. Okay. So here's another way to look at it. Okay. I'm going to start with the same function. I want to keep everything in terms of variable. However, I'm just going to call the first distance x1. Like we know it's 70, but I'm just going to call it x1 because it can be any value at once in future problems, okay? So I want to solve for delta x1, dividing both sides by 2a. So I have a statement for x1. Delta x1 is vi squared over 2a. I understand there's a negative sign here, okay, but I'm just showing you how to do ratio. Well, that's easy to do. We can write the same function again, except on this side, what I've done here is that instead of vi, I actually replaced the new function with 2vi because 56 is twice the speed of 28. Therefore, 2 times vi 2 times 28 is 56. So I know it's 56, but doing it this way just kind of help ease a lot of number crunching. Okay, VF is 0, therefore distributing the 2 to the 2 inside the parentheses, the exponent 2 to the VI gives you negative 4 VI squared. 2 squared is 4. The VI is being squared, so that's that. Here's delta x2. Okay, so what you can do, again, is solve for delta x2. And delta x2, therefore, is equal to negative 4 VI squared over 2a. But here, I hope you recognize by now that you can actually substitute in, okay? Excuse me, this line just came up twice. So you can ignore this line here if you're watching carefully. This line is just a duplicate of the previous line. But what I'd like to point out is that the stuff that I have in black here, VI squared 2a, okay, VI squared over 2a, look on the left side, VI squared over 2a is delta x1. So all the stuff that I'm circling with my cursor, okay, all the stuff right here, the VI squared divided by 2a is my original distance, my baseline, my reference point, delta x1. So it's just 4 times delta x1. But we know that delta x1 is 70, so it would just be 4 times 70, which will give us the same answer of 280. So that's one way to look at it. Sometimes answers don't have to be in numerical format. It can just be this expression, on a quiz or on future assessment where, well, delta x2 is 4 times delta x1. How do you know if it's true or false? Just do the step here, replace the new velocity with whatever coefficient that makes that statement true, and it will always work out, assuming your algebra is good, okay? Other than that, I hope it helps. Stay nerdy, don't be whack.